9.9 Rocket Propulsion. The outline of this video is as follows. We will begin by exploring the fundamental principle of rocket propulsion, which is a direct application of the conservation of momentum in an isolated system. You will see how a rocket can accelerate in the vacuum of space without anything external to push against. Following that, we will step through the mathematical derivation of a rocket's speed, starting from basic momentum principles and arriving at the final rocket equation. We will then define and calculate the thrust, which is the force that propels the rocket forward. Finally, to bring these concepts together, we will work through some practical examples applying the equations we have derived. To understand how a rocket moves, we must first contrast it with a familiar vehicle like a car. A car generates power using its engine, but to move forward, it must transfer that energy to the road. The tires push backward against the pavement, and the road pushes back. Because the car relies on this interaction with an external medium to accelerate, we classify it as a non-isolated system. A rocket in deep space, however, has no road or air to push against. It functions as an isolated system, meaning it does not rely on external forces for propulsion. Instead, the rocket pushes against its own ejected fuel. By defining the system as the rocket plus its exhaust, we apply the law of conservation of momentum to explain how it accelerates internally. To build an intuition for rocket propulsion, let us consider a simple analogy: an archer standing on a sheet of frictionless ice. This scenario helps us understand how an object can accelerate without pushing against anything external. When the archer fires an arrow forward, the arrow gains momentum. Because the archer and arrow form an isolated system, total momentum must be conserved. This means the archer must gain an equal amount of momentum in the opposite direction, causing them to slide backward. We can also analyze this using Newton's third law. The bow exerts a forward force on the arrow. In response, the arrow exerts an equal and opposite backward force on the bow and the archer. This backward reaction force is what causes the archer to accelerate. This is exactly the principle an astronaut uses to maneuver in space, releasing bursts of nitrogen gas instead of arrows. The key takeaway is that propulsion in an isolated system is achieved by ejecting mass, which generates a reaction force on the main body. Rocket propulsion provides a powerful, real-world example of the conservation of linear momentum. The key idea is that the rocket and its fuel form an isolated system. When the engine fires, it ejects exhaust gases backward at a very high speed. This gives the exhaust mass a significant momentum in the backward direction. To conserve the total momentum of the system, the rocket must gain an equal and opposite amount of momentum, pushing it forward. This continuous forward push, generated by expelling mass, is called thrust. While the rocket accelerates, the center of mass of the entire system, including the rocket and all the gas it has ever expelled, continues to move at a constant velocity. It is also important to distinguish momentum from energy here. While momentum is conserved, the kinetic energy of the system increases. This process is like an explosion or a reverse inelastic collision, where the chemical potential energy stored in the fuel is converted into the kinetic energy of the rocket and its exhaust. Therefore, a rocket moves forward by pushing its own exhaust backward. To understand how a rocket accelerates, we will apply the principle of conservation of momentum. Let us carefully define the state of the rocket fuel system just before and just after a small amount of fuel is ejected. Initially, as shown in figure part B, the rocket and all its fuel form a single object. This system has a total mass m and moves at a speed v. The total initial momentum is therefore m times v. A short time later, as shown in part C, the rocket has ejected a small mass of fuel, which we call delta m. This means the rocket's remaining mass is now m minus delta m, and its speed has increased to v plus delta v. The ejected fuel itself now has momentum Its exhaust speed relative to the rocket is v sub e. To find its velocity relative to a fixed observer on Earth, we subtract this from the rocket's initial velocity, so the exhaust gas moves at a velocity of v minus v sub e. By defining the momentum for each piece in the initial and final states, we can set up our conservation equation. To derive the equation for rocket motion, we will apply the principle of conservation of momentum. We treat the rocket and its fuel as a single, isolated system. First, let us look at the initial momentum at time t. The rocket has a total mass, capital M, and moves at a velocity, v. So the initial momentum of the system is simply m times v. Next, consider the system a short time later, after a small mass of fuel, delta M, has been ejected. The system now consists of two parts. The rocket's mass has decreased to the quantity m minus delta M, and its velocity has increased to v plus delta v. The ejected fuel has a mass of delta m. Its velocity relative to the Earth is the rocket's velocity v minus the exhaust speed v sub e. Because the system is isolated, the total momentum is conserved. We set the initial momentum equal to the final momentum, which is the sum of the rocket's momentum and the ejected fuel's momentum. This gives us the fundamental equation shown on the slide. Now we will use the conservation of momentum principle to find an expression for the rocket's change in speed, delta v. The first long equation on the slide comes from setting the initial momentum, m times v, equal to the final momentum of the rocket and its ejected fuel. After multiplying out all the terms, we can simplify the expression. The initial momentum mv on the left cancels with an mv term on the right. The terms involving v times delta mim also cancel out. This leaves a much simpler relationship, which shows that the change in the rocket's momentum is directly related to the momentum of the exhaust. After a final rearrangement to solve for the change in velocity, we arrive at our key result for this step. This equation tells us the rocket's change in speed resulting from the ejection of a single, small portion of fuel mass. To accurately model a rocket with a continuously firing engine, we must adapt our previous momentum equation using calculus. We do this by considering an infinitesimally small time interval. In this limit, the finite changes, delta v and delta m, become the infinitesimally small differentials, d, v, and dm. A key simplification also occurs. The term representing the product of these two small changes, dm times dv, is negligible compared to the other terms, so we can ignore it. This simplifies our momentum balance to mdv equals vdm. Finally, we must relate the ejected mass to the rocket's mass. The mass of the exhaust, dm, is mass that the rocket has lost. Therefore, the change in the rocket's mass, dm, is the negative of the ejected mass, so dm equals negative dm. This gives us the fundamental differential equation for rocket motion. mdv equals negative v times dm. To find the total change in the rocket's speed, we now solve the differential equation we just derived by integrating it. We integrate the left side with respect to velocity, from an initial speed v to a final speed vf. We integrate the right side with respect to mass, from the initial total mass mi to the final mass mf. Assuming the exhaust speed v is constant, this integration yields the celebrated Tsiolkovsky rocket equation. It states that the change in speed, Vf minus Vi, is equal to the exhaust speed V multiplied by the natural logarithm of the mass ratio, Mi over Mf. This equation is powerful because it tells us exactly what determines a rocket's performance. The final speed depends on two key factors. First, it is directly proportional to the exhaust speed, so we want engines that eject gas as fast as possible. Second, it depends on the logarithm of the mass ratio. This means that to get a large change in speed, the ratio of the initial mass to the final mass must be extremely large. For example, to reach orbit, a rocket's mass must be over 90% fuel. Therefore, a rocket's speed is maximized by having a high exhaust velocity and carrying a large amount of fuel relative to its structural mass. Let us now define the propulsive force on the rocket, known as thrust, and see how it is calculated. Thrust is simply the reaction force exerted on the rocket by the high-speed exhaust gases it ejects. From Newton's second law, we know this force equals the rocket's mass times its acceleration, which is the quantity m times dv divided by dt. Using the relationship we found on the previous slide, we can express the magnitude of the thrust as the product of two key terms. It is the exhaust speed, v, multiplied by the rate at which the rocket's mass changes. This rate, the magnitude of dm divided by dt, is called the burn rate, the pushback of a powerful garden hose. The pushback you feel is the thrust, and it increases if the water shoots out faster or if you increase the flow rate. Therefore, to generate a larger thrust, a rocket must either eject its exhaust at a higher speed or burn its fuel at a faster rate. Now let us apply the rocket equation to a practical example to calculate a rocket's change in speed as it consumes fuel. In this problem, a rocket is already moving with an initial speed, v(i), of 3,000 meters per second. It ignites its engines, expelling exhaust with a speed, ve, of 5,000 meters per second relative to the rocket. Our goal is to find the rocket's final speed, vf, at the moment its total mass has decreased to half of its initial mass. We use the rocket equation, vf equals vi plus ve times the natural logarithm of the fraction mi over mf. The problem tells us that the final mass, mf, is equal to 1/2 of the initial mass, mi. Therefore, the mass ratio mi over mf simplifies to exactly 2. Plugging in the numbers, the final velocity is 3,000 plus 5,000 times the natural logarithm of 2. This calculation yields a final speed of approximately 6,500 meters per second. By ejecting half its mass as fuel, the rocket significantly increased its speed. Now for the second part of the example, let us calculate the thrust on the rocket. Thrust is the propulsive force that the ejected exhaust gases exert on the rocket, pushing it forward. The equation for thrust is given by the product of two quantities, the exhaust speed relative to the rocket, which is v sub e, and the rate at which the rocket burns fuel, which is the magnitude of the change in mass over time, or dm over dt. From the problem description, we know the exhaust speed is 5.0 times 10 to the power of 3 meters per second. We are now given that the fuel burn rate is 50 kilograms per second. To find the thrust, we simply multiply these two values together. Multiplying the exhaust speed by the burn rate gives us a final thrust of 2.5 times 10 to the power of 5 newtons. This shows that the force accelerating the rocket is directly proportional to both the speed of the exhaust and the amount of fuel burned each second. Let us apply our understanding of thrust to a practical example involving a fire hose. This problem shows how the principles of variable mass systems are relevant even in situations where the goal is to prevent motion, not create it. The problem asks us to find the speed of water exiting a hose, given that two firefighters apply a total force of 600 newtons to keep it steady. As water is ejected from the nozzle, it creates a thrust force on the hose, pushing it backward. This is the same principle that propels a rocket. However, unlike a rocket which accelerates, the goal here is to keep the hose stationary. This is a condition of equilibrium, where the net force is zero. Therefore, the force applied by the firefighters must be equal in magnitude and opposite in direction to the thrust from the water. To proceed, we first need the mass flow rate. The problem gives a volume flow rate of 3,600 liters per minute, which converts to 60 liters per second. Since 1 liter of water has a mass of 1 kilogram, the mass flow rate, or the magnitude of dm/dt, is 60 kilograms per second. The force required to hold the hose steady is a direct measure of the thrust produced by the water. Here we will calculate the speed of the water exiting the fire hose. The key is to recognize that the stream of water creates a thrust force, just like the exhaust from a rocket. The equation for this thrust is the exhaust speed, v, multiplied by the mass flow rate, which is the quantity dm/dt. For the firefighters to hold the hose steady, their force must exactly balance this thrust. This means the thrust is equal to 600 newtons. Next, we need the mass flow rate. The problem states the water flows at 3,600 liters per minute. Since 1 liter of water has a mass of about 1 kilogram, this is equivalent to 60 kilograms per second. Now we can rearrange the thrust equation to solve for the speed. The exhaust speed, v, is the thrust divided by the absolute value of the mass flow rate. Plugging in the values, we get 600 newtons divided by 60 kilograms per second. This gives a final result for the water speed of 10 meters per second. This slide summarizes the two fundamental equations that describe rocket propulsion, which is a direct application of the conservation of momentum. First, we have the ideal rocket equation. It shows that the change in a rocket's velocity is the product of two factors: the speed of the exhaust gases relative to the rocket, v sub e, and the natural logarithm of the mass ratio, m initial over m final. To achieve a large final velocity, a rocket needs both a very high exhaust speed and a design that maximizes the fuel-to-structure mass ratio. In other words, the rocket's final mass, after all the fuel is burned, should be a very small fraction of its initial mass. Second, we have the expression for thrust. Thrust is the instantaneous force that accelerates the rocket. It is equal to the exhaust speed multiplied by the magnitude of the rate of change of the rocket's mass. This rate, dm/dt, is commonly known as the burn rate. To generate high thrust, an engine must expel a large amount of mass per second at a very high speed. Let us wrap up by applying these concepts to two review questions. The first question compares two factors in the rocket equation: the exhaust speed, v sub e, and the mass ratio. The equation tells us that the change in the rocket's speed is directly, or linearly, proportional to the exhaust speed. In contrast, the speed change is proportional to the natural logarithm of the mass ratio. This logarithmic relationship means that large increases in the mass ratio yield diminishing returns for the final speed. Therefore, the exhaust speed has a more direct impact. The second question revisits the firefighting example. If the nozzle is made smaller, the water's exit speed increases, while the mass flow rate remains the same. The thrust is the product of the exit speed and the mass flow rate. Since the speed has increased and the flow rate is constant, the thrust must also increase. The firefighters must apply a force equal to this thrust to keep the hose steady. Thus, making the nozzle smaller requires the firefighters to apply a greater force.